Hi, Doc Revis here. In this video, I will show you how to solve problems using the Clausius Clapeyron equation. This slide shows you the Clausius Clapeyron equation. Notice I have several variations of this equation. Oftentimes, the Clausius Clapeyron equation is treated more as a math problem than it is a chemistry problem. Therefore, you will see many different forms of the equation. But rest assured, any one of them will get you to the same solution. So we have four of the variations shown on the left side of this slide. In the middle, we have a popular variation of this where we solve for delta H. We also have, on the far right, the pressure equation. Note also that temperature is in Kelvin when doing Clausius Clapeyron equation problems. Note that when solving Clausius Clapeyron equations, it's very important that you use joule per mole for your delta H values because of the R value. So let's work a problem. At 34.0 degrees C, the vapor pressure of isooctane is 10.0 kilopascals. And at 98.8 degrees C, the vapor pressure is 100.0 kilopascals. What is the enthalpy of vaporization of isooctane? A useful thing to do in working any of these problems is to mark off the problem with the variables. Here we note that we have a T1, a T2, a P1, a P2, and we're looking for delta H of vaporization. Therefore, we write out all our givens, or we circle them in the problem, and we write out the Clausius Clapeyron equation, and we match those variables. One of the things we must do to solve this problem is rearrange the equation to solve for delta H. So we show you that rearrangement of the equation. We then plug in all of our variables from the problem, and we obtain 33,800 joules per mole. That is equal to 33.8 kilojoules per mole. It's important to note that R for the Clausius Clapeyron equation is 8.314 joule per mole K. Let's work another problem. The vapor pressure of a liquid triples when the temperature is increased from 25 degrees C to 45 degrees C. What is the enthalpy of vaporization for the liquid? We first mark off all the variables from the problem, and we note that the temperature is converted to Kelvin. It's important to note that temperature must be in Kelvin when solving these problems. So we clearly have T1 and T2 in degrees C, which we will convert to K by adding 273. We note also that we don't exactly have the pressure, but we do have an indication of the ratio of that pressure. And the ratio of that pressure is 3:1. Therefore, we can use that ratio where P2 would be 3 units, or just the value of 3, and P1 would be 1 unit, or simply 1. We rearrange the Clausius Clapeyron equation as shown here to solve for delta H. We then put in our R value, 8.314 joule per mole K. We then take the natural log of the ratio of 3:1 divided by the difference between the inverse of the temperature in Kelvin. When we punch this value through our calculator, we obtain 43,280 joule per mole, which is 43.28 kilojoules per mole. However, if we consider that there are two significant figures in this problem, then our answer would be 43,000 joule per mole, or 43 kilojoule per mole. It's important to note that on occasion, students will be confused about significant figures when doing Clausius Clapeyron equation because they will typically be using temperatures and they will be using pressures. The default position is to assume that the significant figures in the temperature are the significant figures to be used. Let's work another problem. For benzene, the normal boiling point is 80.1 degrees C, and the enthalpy of vaporization is 30.8 kilojoules per mole. What is the boiling point of benzene in Denver, where the atmospheric pressure is 83.4 kilopascals? We immediately mark up our problem to find our variables. We notice we have delta H vaporization, T1 in degrees C, which we will convert to K. We have T2 in question. That is what we're looking for. That's the unknown. We have 83.4 kilopascals for P2. We also have P1 indirectly when it states that it is the normal boiling point. When we talk about normal in terms of Clausius Clapeyron equations, normal means 1 atmosphere or 101.3 kilopascals. So since we've identified our variables, we take the Clausius Clapeyron equation, we rearrange it to solve for T2, or we put in all the variables and solve for T2 at the end. Either process will work as long as the math is done properly. So we take T2 and we have it rearranged, and we note that it is the inverse of the equation shown here. We take all of our values and we put those values in their proper place. We note that we're taking the natural log of the ratio of the pressures times R divided by delta H vaporization plus the inverse of the temperature in degrees Kelvin. That entire expression is equal to 0.002882671. We simply invert that value and we obtain 346.9 K or 73.8 degrees C. So let's work another problem solving for T2. The vapor pressure of water at 290 K is 23.8 millimeters of mercury. At what temperature is the vapor pressure of water 1075 millimeters of mercury? As we always do, we mark up our problem with the variables and we note that T2 is the unknown. We have our T1 at 298 K, therefore no conversion is necessary there. We have P1 in millimeters of mercury, and we have water in millimeters of mercury. Since the units are the same, we're happy to use them as they are. We went to a table and we obtained the delta H vaporization of water to be 30.8 kilojoule per mole, which is equal to 30,800 joule per mole. Note that when solving Clausius Clapeyron equations, you must use joule per mole because of the R value. It's very important that you use joule per mole for your delta H values when solving the Clausius Clapeyron equations because of the R value. So, now that we have the problem marked up, we then take the Clausius Clapeyron equation, we put in all the values, we then work through the math step by step. Note that we're taking the natural log of the ratio of the pressures. Note that our R value is in joule per mole K. Therefore, our delta H must be in joule per mole. We take the difference between the inverse of the temperatures, with T2 being our X, or our unknown variable. We work these values through and we obtain at the end T2 of 383 K. Don't hesitate to pause the video and walk through each step with the math. Let's work a problem where we're calculating pressure, P2. Mercury has a delta H vaporization of 61.4 kilojoule per mole at 80 degrees C and 0.0888 torr. What is the vapor pressure at 160 degrees C? So we mark up our equation with the variables. We note that we have P2 as the unknown. We're given the delta H of vaporization, and we have T2, T1 in C that we must convert to Kelvin, and we also have P1 in torr. Since our R value is in joules per mole K, we convert our delta H of vaporization to 61,400 joule per mole. Then we take the Clausius Clapeyron equation. We put in the values for each of the variables shown here, where we have P2 over the torr, and we'll take the natural log of that ratio. We have our delta H vaporization over our R, and that's multiplied times the difference between the inverse of our temperatures. We then use our calculator to punch the numbers through, and because we're working with a natural log, and when we move the natural log to the other side of the equation, it becomes e to the power of minus 3.86. When we punch that value through, we obtain 47.5. So P2 equals 47.5 times 0.0888 torr, and the torr units were the only units to survive the math. And so our final answer is 41.21 torr. Let's work another problem. The vapor pressure of water is 1 atmosphere at 373 K, and the enthalpy of vaporization is 40.4 kilojoule per mole. What is the vapor pressure at temperature 363 K and 382 K respectively? So as is our practice, we mark up the equation with our variables, and we note that we have a P1, 1 atmosphere, we have T1 at 373 K, therefore no conversion is necessary. We have delta H vaporization in kilojoules per mole, and we remind ourselves that that must be converted to joule per mole simply by moving the decimal 3 places to the right. We note that we have 2 T2s. We have the first set of T2s, and we have the second set of T2s, and P2 is in question. When we write out these variables, we recognize that we're working 2 problems, and that's important to note, that you're actually looking for 2 solutions. You're looking for the solution with 363K, and you look for the solution with 383K. These problems are treated as 2 independent problems. We use the pressure equation as shown here, and we set that up for problem number 1, involving the first temperature of 363 K. When we put our values in, note that again the delta H vaporization is converted to joules because our standard R for Clausius Clapeyron equation is to have it in joule per mole K. So we take that ratio, we do the math, and we obtain 0.697 atm. Likewise, we will solve the second problem for P2 involving K of 383. When we put those values in, we punch it through our calculator, we obtain 1.41 atmosphere for P2. So when a problem involves having 2 separate temperatures, you're going to work this as two separate problems. Let's work a problem where we solve for delta H involving a pressure change. Keep in mind that although we're solving for delta H vaporization, this could be just as easily a delta H of fusion or any other delta H. So let's restate the problem. Calculate delta H vaporization for ethanol with a vapor pressure at 40 degrees C of 150 torr. The normal boiling point of ethanol is 78 degrees C. We mark up our problem shown here, where we have automatically converted the temperature from C to Kelvin by adding 273. Our heat of vaporization is the unknown. We have P1 at 150 torr, and we have T2 of 78 degrees C plus 273. Note also that the term normal defines the pressure at 78 degrees C. Normal pressure at 78 degrees C for ethanol is 760 torr, or 1 atmosphere. So be aware of the terms normal. Normal tends to mean 1 atmosphere, or 760 torr, or 760 millimeters of mercury. So now that we have identified the variables, we use the Clausius Clapeyron equation, and here we have to rearrange this equation to account for these two pressures. So be aware, in a problem like this, you'll use a rearranged form of the Clausius Clapeyron equation to account for the two pressures. So essentially, when there are two pressures, you would take the log of P2 minus the log of P1, and you would then solve it through the equation. Also note that for convenience, we've used one of the other forms of the original Clausius Clapeyron equation. So we take the Clausius Clapeyron equation, we set it up where we take the difference between the natural log of the pressures, and the natural logs are obtained by simply putting the values into your calculator. We set up the equation, we put in all the variables with delta H vaporization being the unknown. We then solve as many of the parentheses as we can. We simplify down, and we obtain 39 kilojoule per mole for delta H of vaporization. So again, in a problem where we clearly have both temperatures and we clearly have two pressures, we must remember to take the difference between the log of those two pressures to solve the problem for delta H vaporization. So there you have it, solving problems using the Clausius Clapeyron equation.